All right. So I am Philip Lira. I am a senior engineer at Black River Studios. Do mostly graphics there. And today I'm going to talk about how we optimized our game, Finding Monsters Adventures. So first, I think a lot of people already saw the game at the conference, but I would like to show the video to you. So our game is about two siblings that they get sucked into a world and this world is missing parts, so they get a magical camera, and they have to collect the missing parts of this world by taking pictures of monsters. And we have 3 worlds. It's a total of 21 stages. To get this nice look and feel and art, we used custom shaders. So pretty much all of the shaders we've done are custom. And we have grasslands, icelands, and moorlands, and we have different monster mechanics. So they each behave differently. And we have nice gameplay modes like selfie mode. So that's it. The game will be released next month for Samsung devices first, and at the end of the year for more Android devices. So I'm going to talk about first a few of the technical challenges we had for this game, which is we had a lot of custom lighting models and custom VFX. This is one shot from the grasslands overroad, so there's a lot of levels there. So our UI, it doesn't have all a 2D UI, so it does, the kids, they traverse the world as they go. And so we had to do effects like this water shader, but still keep the look of a cartoonish effect. And we also have things like ice shaders. And we have, in the same scene, multiple characters. And for instance, this character has 69 bones and 4 blend weights, 4 vertices influenced by each bone. So our motivation is we want to push as much content we can do in the devices without impacting the gameplay and no overheat. So at mobile, we're also concerned about the devices getting hot, right? Because when the device gets hot, then it takes you a lot of battery time and it gives you a bad experience. This is a short talk, so I'm going to talk about a few things. So I won't be able to talk about all of it. So the question we want to ask is, can we get the same quality with a similar approach? So for instance, we have artists at Black River, technical artists, that they alter some shaders, most of them, I would say. And then when I get to optimize them, I go for a slightly different solution. So I go to them and ask, okay, I have this solution for you, but then we have to change a few of the material properties and a few of the textures. Is that okay? And then we sit down, we talk through it, and we get about the same effect, much better for the device. And if you fail at this, if you hit the limit, our budget, then either the gameplay or the visual quality will be impacted. And from my experience, it always goes to the visual quality. And I've done projects before that at the very end, we didn't hit our target, and we had to remove a lot of things. And when it comes to that case, it hurts because you worked so much to get that nice effect. So when it comes to the case that we had to remove things, trust is important because at Black River, the technical artists, they trust me, and they know that I'll do my best to get the exact same effect they want there. And when I come to them and say, we have to simplify this and remove a few things, they know that I'll probably tried all of it before reaching this. So I'm gonna do first a first brief introduction about the optimization process, and then I'm gonna start talking about a case study of a scene we did. Okay, so I'd like to break down in three major steps. So first, a golden rule is when you're optimizing something, do not make any assumptions. So we tend to make assumptions like we look at really nice effects and say, those effects might be getting the most milliseconds of my game. But do not make assumptions like that, because even a simply blob shadow, for instance, might be taking your FPS and those precious milliseconds you need. So a golden rule is use a profiler. A profiler will tell you where the bottleneck is. And if you're not optimizing the bottleneck, then you're wasting time. So as soon as you find your bottleneck, what you're going to do is you can rewrite the code to use less resources or use them more efficiently. Or you can often fake things and simplify. So sometimes you don't need many dynamic per pixel lights, right? So you can simplify it with different effects, or parts of the shadow can be added dynamically with boxes or quads there. So in those cases, the experience comes a lot into play to make decisions to optimize hot zones. So after you did a profile and optimize it, you need to test to see how much you saved. So one thing you have to be really careful is you need to guarantee that the first environment or the first scenario you profile has to be the same exactly scenario you test, or you might get different results. And that might get tricky, but we try to get exactly the same scenario. So, and you have to ask yourself, how many milliseconds did you save by that? Okay, so how to find the game bottleneck? Unity comes with a built-in profiler. I think most of you are used to this, and it does most of the work. But when it comes to the GPU, we like to have more detailed info. So for this project, we used dedicated GPU profilers. And for the target we have, for instance, for Snapdragon GPUs, you have Adreno profiler. And for the ARM Mali GPUs, you have the Mali graphics debugger and a DS5 streamline, which are two different tools to achieve the GPU debugging and profiling. So I'm going to go to use for this the Adreno GPU profiler. So this is the look and feel of the scrubber view. So on the scrubber view, I can capture a frame and see detailed stats per draw call. And I can also see all of the textures, the texture compressions, and I can click on each individually draw call to see the shaders, how much work they're doing, and I'm going to show more pictures. One interesting thing is that Unity 5 will come with a draw call step, which will help a lot for a few things. So suppose I'm using Adreno Profiler. It also comes with overrides. So I can go in Adreno Profiler and disable GL. So it will disable all OpenGL calls. And this is a simple flowchart. So for instance, if I disable GL and the frame rate increases a lot, now, if the frame rate doesn't increase a lot, then I am CPU bound. If it does increase a lot, then I'm GPU bound. And that can be, on the GPU pipeline, a few macro stages that I've broken down there. But it can be Vertex fragment shading, and you can be memory bound or bandwidth it. So for instance, on the Vertex, you might be pushing too many triangles to the GPU. You might have custom vertex shader effects, like you might be bending geometry. At Black River, we prototyped some curved rolls, and we were doing vertex offset in the vertex shading. And you can be using per vertex lighting. Unity support up to 4 per vertex lighting. So if you might have too many lights in the scene. Or you can be fragment. It comes down to the fragment shader, how many instructions you have, how many texture samples you do, the blending operations, and for instance, per pixel lighting, if you're using forward rendering tracing. So at the quality settings, you can set the maximum amount of per pixel light you have in the game. Or you can be bandwidth. That is, you're using large textures, uncompressed, and no bitmaps, or the dependent texture reads, which is you sample a texture to do another sample in another texture. And that's bad for the GPU because the GPU tries to cache the UV that comes from the vertex. That saves a lot. But if you do dependent texture reads, you have some overhead there. And block resolvers, which is rendered textures, like you're rendering through big rendered textures. You're doing things like grab pass. Grab pass is awful for mobile. Things that you need the GPU to stop to read something. So I'm going to show a case study of one of the scenes of our game. This scene is called Royal Moon. And in this scene, we have 106K triangles. We have 87 draw calls. We have an overdraw factor of 2.51. And I'm going to say to the ones that don't know what the overdraw is, I'm going to get into that on the next slide. And on the shader stats, the heaviest shader, we have 160. ALU is like math instructions, so like times and divide and interpolations, blends, things like that. And up to 7 texture samples, so that's a lot. So you can see, as vertex-wise, we're not that complicated, right? But on the fragment, we have a lot. So the Arduino profiler, it tells me, it has a counter, and it tells me that the percentage of time shading fragments is at the max compared to the percentage of time spending on the other GPU resources. So that's clear to me that we are fragment bound, and that's where we're going to dive in deep. So first I run Overdraw debug, and this view is a picture. How do you read it? So when you render something and you render again, you're rewriting a pixel, and we call that overdraw. So on the overdraw debug, instead of rendering the actual pixel, you render an additive color. So the white zones means they're the hot zones for overdraw. And you can see, for instance, that the monster is being rendered, and then the background, the background is being rendered, and then the monster is rendered on top of it. So it adds to the background already rendered. So in order to improve this, I'm going to talk about rendering order, which matters for performance. Because, so for instance, if I draw something that is in front and I draw something later that's occluded by that, I can have a z-test that tests that the pixel won't be visible, and then I can discard this. We call it early z-test. And so the render order, it matters. And the optimized render order will be something like this. All of your opaque geometries, you want to render them front to back, okay? And Unity does this for you. So Unity runs a sorting algorithm that gets the pivot point and ordered it front to back. But sometimes, because the pivot point might not be on the good spot, or your mesh might not be good for it, you have to assign to manual layers, which I'm going to say in the next slide. So we do opaques front to back. We do the skybox. And then we do transparent back to front. And that is because when I do a blend, I need to have the thing that's behind it so I can blend the ones in front. And at last, we render the overlay, which is a UI head. So in order to improve the overdraw, we need to improve opaque rendering. Okay, Unity allows us to set sorting layers. So I can set opaques into different layers, and I guarantee that the layer 0 is going to be rendered always before the layer 1. And you might be acquainted with the 2D UI, right? Because you can sort that. But you can also do that for 3D. And the question we want to ask is how we assign objects per layer. And if you do it by shader, which is a render QE you have on the shader, that's not the best solution, because whenever you want to assign objects with the same shader on different layers, you have to duplicate the shader. And that increases the GPU resources. Those shaders have to be compiled again. So per mesh is not also a good option, because that's not scalable. It requires a lot of work. And because you change the layers, you break the batching, right? So because there's a lot of meshes, you might be breaking batch by mistake. So per material, I'd say yes, per material is controllable. You can create materials for each scene, and then when you change the other layer in a material, it doesn't affect the other material in the other scene. And that's the way we did. So Unity allows you to set a material render QE on script, but we wanted our artists to have a nice and intuitive way of doing this. So what we did is Unity also allows to expand the material editor. And we created a class, a script class called BRS Material Editor that add this to the material inspector. So you can just click override sorting, select the layer, and the order in that layer. And all you have to do after you created the script is add that line to the end of the shader. And then when Unity compiles the shader, it will add those options in the inspector. So the final rendered order we did was we got all the character and props in a first layer, and Unity sorts them in this layer. After we did this, our game has a fixed camera, so we did the ground that the camera is on after. Then we rendered the outer islands. We rendered the planets. And at last, we rendered the sky dome. So this was before and after on the overdraw. So you can see the character now, it gets rendered first, and then after, it renders the ground. But because the z-test happens there, so there's no overdraw. And we reduced from 2.51 to 1.91 overdraw average. This is another view you can get from Arduino, which is the ZReject. So every time a pixel is discarded, it adds a red value. So you can see there are much more red zones there. And in this view, you can see there are islands beneath this ground. They're getting rejected in both views, right? But the ones here are stronger. And the white ones, they mean no rejects at all. That's the particle effects. So we have to, that's alpha blend when we have to sort them, or we have to render them anyway. So also you can see there that the planets there, the planets on the first screen, it's all white. So no discard that. But on the second one, there's a huge part of pixels there that's getting discarded. So the next part is we went to the Fragment Shader to optimize the most hot shaders in this scene. And this is a view of Adreno. So you do a capture frame, and then it lists you all of the draw calls. And then you can click, for instance, this view I sorted for fragment shaded, the shader that shades more fragments. Yeah. So you can see on the picture it's really dark to see, but the ground is red, while the others are yellowish. So the ideal look you want to have here is green and yellows. So the red seems to one good candidate to optimize. And this is the math instructions per fragment. So you can see there are about 154 fragment instructions, math instructions per fragment, and the character is the most heaviest shader. The character is not only, he's not the shader that's contributing to most of the time spent in shading because it doesn't cover as much pixels as the ground does. But he's a really good candidate to be optimized. So how do we optimize for shaders? So for instance, when you do operations on the fragment, they're really expensive because you're running for a lot of pixels. And doing on Vertex, that's better because you usually have less vertices than pixels. And doing per draw call or per model would be best because you do only once. So for instance, you can save computations like if you're passing a rim light and to your shader, you can normalize this rim light on the script and pass it as a uniform to the shader instead of doing the normalization on the shader. If you're doing things like scroll offset, you can also do that. And for instance, there is a monster that we use the custom inner light that gets flickering, and we use the Fourier transform, and we done it on the script, computes the Fourier transform, and pass it to the shader. So it's only computed once per the draw call. So things that we can move from fragment to vertex. So for instance, if you know your textures, you might have like 4 textures, and all of them use the same texture tile and offset, you can do the tile and offset on the shader. So you pass the same tile and offset to the fragment shader. And once, for the operations that they need to be done on the, per pixel, what you can do is you can do equation simplifications. That's basically equations, how to rewrite them to use less math operations. You can use half and fixed precision for mobile because they usually, for some GPUs, they give you better thermal consumption. So that will save you overheat. And there's a question about saturate and max 0 dot. So the saturate gets you between the values 0 and 1, and the max would get basically the same thing. But some GPUs, they have an operation. So for instance, a dot product saturate that they do on the same instruction. So in those cases, the max would be 2 instructions, would be more instructions than the saturate. So in our case, we had many custom shaders done in Shader Forge. And I didn't start the project at the beginning. So when I get to optimize it, there was a lot of shaders in Shader Forge. And Shader Forge does a lot of heavy operations on the fragment. And it's a really nice tool, but it works on all of the general cases. And also, we had many variants of these shaders, and they didn't produce the same code because when the technical artists were altering the shaders, sometimes they changed a little bit, although it's exactly the same algorithm or same shader. But when I get to optimize and see the code, they were different. So how to optimize them all? First, we did a pass on the shader forge itself. And second, I optimized after the shader forge optimization, I did an optimization in code. So I identified the core changes to the lighting model with the artist. So for instance, they have the blink phone wrapped, and they have blink phone with texture ramps to get the cartoonish effect. I created a custom node for those core shader techniques. And the artist helped me a lot with that. So this made the shader code more common and more organized when I got to optimize it. And this is the shader forge is nicely that because it's nice because it allows you to do that. So that's what we had for blink phone and warp. And one major complaint of the artist was that shader forge didn't support custom light maps in the custom lighting. So we created a light map, but the problem is the shader forge does not expose interpolated data, so I had to get the UV there. And after that, I'm going to optimize it. So I'm going to move this UV, offset, and tile to the vertex. Right now, that way is done on a fragment. So at the end, the shaders in the code, we created a lot of macros. And because shader forge creates, it has a convention for the name, I was just replacing the macros. So you can see I have a macro for tangent space, view direction. I have the blink from wrap, which is the same box I had before. And I have there our custom material editor. So the results is, I'm going to go real quick with this. At the end of these optimizations, we did 21 reduction on the alu fragment, which was 90 for the ground shader and 71 for the, it went to 90 to 71. 45% reduction on the fragment shader, on the fragments shaded, not shader, I'm sorry. And 64% fragment instruction, and overall improvement of 7 milliseconds on the GPU. I'm going to skip this because we're going out of time. And so the texture compression we used for this project, ASTC, it gives you best performance and high quality. It improves the bandwidth and power consumption, but only a few devices are supported. So Node 4, S6, and above support this. And you have to be really careful because if you build for ASTC or another texture compression that's not supported by your device, what the GPU will do is uncompress the textures so it can run it. So they'll be really bad. And Unity supports ASTC on the OpenGL3 profile and for Android 5 devices. So that's a comparative between ASTC 4, 6, and ETC 2. You can see their better quality. This is the recommended settings. So you used RGB. For RGB, you used 6x6 blocks, and RGBA, we used 4x4 blocks, as well as normal maps. And our review is, do not, when you're optimizing, do not make any assumptions. Use a profiler to find your bottleneck, or else you do wasted work. GPU profilers give you in-depth data about per draw call, as you saw some of the stats. You can assign objects per sorting layers, so you help Unity make the work for you. Oops. You can reduce the amount of work of optimizing shaders by creating ways to reuse the code. That's what we did with the node and with the macros in include file. And ASTC texture compression gives you the best option available for quality, but it's not supported for all devices, so you have to be careful. And now I'd like to, if anyone has questions, I'd like to take it. Hi.
Does it ever run into problems with the inclusion mapping to track the origin as opposed to a bounding box? Do you ever have that fail
Okay, he's asking about the occlusion mapping problems we had for this project. Uh, Not that I am aware of. So at Black River, we have technical artists that they deal with the occlusion culling. So nothing that they came up to me to report anything. Hi?
When you started to kind of go through the shader forge stuff and help them arrange things better and optimize, is it easier for them the next time if they want to make a new one to kind of follow those same steps again, or would you still have to come through and kind of do another pass with it later?
Okay, so he's asking about the shader forge and kind of the best way to approach optimization with it. So yeah, I didn't start at the beginning of the project. So for this project, we didn't have budgets. We did the benchmarks on the devices we had. So for the next projects, what we're going to do is I'm going to sit down with the technical artists and I'm going to talk to them what lighting models you want to achieve. So I'm going to do those boxes in the shader forge, like the blink from wrapped and whatever they need, we're going to discuss. And then they can use this for prototype or everything the effect they want to achieve. And when I get to optimize them, it'll be much less work. Okay. So you can follow us. We're Black River Studios. That's the website, Twitter, and Facebook. You can also follow me on Twitter. My Twitter is filira. And that's it, guys. So thank you for coming. I appreciate that.